We've made it to Chapter 13, Chemical Equilibrium. I'm hoping that by accident you fall in love with chemical equilibrium. And if you do, we'll be doing equilibrium from now until spring break, so you're just going to love it. Actually, I'm kind of serious about that. If you get this chapter, we're just going to apply it to different situations between now and spring break. We'll apply it to acids and bases and precipitates and all kinds of good things. So I suppose we should figure out what equilibrium means, right? Okay, check out this equation in the middle. Hydrogen reacts with oxygen to form water. Most reactions that you've seen in your chemistry career look like this. You've got reactants, they form products, the reaction stops. Done deal. Now either you completely react the reactants to form products, or maybe there's a limiting and an excess, and so you react them as completely as possible to form as much water as possible, and you might have a little excess hydrogen or oxygen. But we say there's a total formation of products. The forward reaction is favorable. Hydrogen and oxygen want to react together and form water. This might also be written then as the reaction goes to completion. Again, meaning that we react them as completely as possible. And we might have a little excess hydrogen or oxygen, but we'll form the maximum amount of water possible. Okay, check out now this calcium oxide reaction. The way that it's written, you'd think that calcium oxide goes forward and decomposes to form calcium and oxygen. And that can happen. However, it's just not favorable. Do you remember this equation? This was from a while ago. Q1, Q2 over R. You remember that thing? You never had to really do calculations with this. It's Coulomb's law. It helps us kind of evaluate the strength of ionic compounds, attraction between ions, or we can use this to rationalize like the attraction between like a nucleus and electron cloud, all that good stuff. Well, Q1 and Q2 are the charges, so calcium and oxygen are +2, -2. The stronger the charges, the more energy required to split the ions. And then R is the distance between the two ions. Oxygen is definitely a small atom. Calcium's kind of moderate. But overall, this calcium oxide has a pretty strong Coulombic attraction. Look at that, spitting out the big words, huh? There's a really strong attractive force between the calcium and oxygen ions. So can we decompose it? Sure. It's just not favorable. We would need to add tons of energy. This would be highly endothermic. So they're pointing the arrow toward the calcium oxide just to show that going forward is not favorable. The calcium oxide is more stable. Now we hit this last example, this nitrogen and oxygen example. Look at the arrow. It's double-sided. I don't know if we've seen a whole lot of these double-sided arrows yet. This is the good stuff. We have mentioned in the past that sometimes a reaction starts out, you form products. As the products become more concentrated, there is the chance that they could collide with each other. If those product particles collide, sometimes the reaction shifts in reverse. It goes backwards, and those product particles reform the reactants. Whoa. Here's what equilibrium is. Now, you see the word equilibrium, and you think something's got to be equal, right? Yes. It's the rate, the forward rate equals the reverse. This thing is going forward and backwards at the same time. We're forming products and we're reforming reactants all at the same time. It's magical. What's equal about equilibrium is the rate going forward equals the rate going reverse. By accident, some people will say at equilibrium you have equal amounts of things, like equal amounts of reactants and products. If this thing is going forward and reverse at the same rate, your products and reactants will be present at the stoichiometric ratio. They will not be equal amounts, unless it's all 1-to-1 ratios. The thing equal about equilibrium is the rate. The rate at which this thing goes forward equals the rate at which this thing goes in reverse. I'll show you this reaction in class. It's actually kind of cool. This nitrogen dioxide is a brown gas. It's actually toxic too. That'll be fun. This one's colorless. If this reaction had a total formation of products, if it was just a one-sided arrow forming the products, I should start with brown gas, I should form colorless gas, reaction stops. That's not the case. When this thing is at equilibrium, it's going to kind of look, I don't know, it's like light brown, kind of an orangey brown color. At equilibrium, you'll have 2 parts brown gas, 1 part colorless gas. So it does lighten. As the reaction starts going, it does lighten. At equilibrium, though, it's not just all colorless gas. It's mostly brown gas. The forward and the reverse happen at the same rate. Which brings us then to this concept of dynamic equilibrium, that once that thing is at equilibrium, you're not going to see the color change anymore. Initially, you're going to see it get a little lighter because you start forming products, that lighter gas, the colorless gas. But then as the products go back to the reactants, eventually the color stays constant and you don't notice a change anymore. But that doesn't mean that there is no change. It doesn't mean that somehow the reaction stopped forming products or reactants. It just means that we've hit dynamic equilibrium, where the rate going forward equals the rate going in reverse. So you have a constant concentration over time. You would have 2 parts brown gas, 1 part colorless gas. The same kind of thing happened when we were talking about vapor pressure, how particles on the surface of a liquid in a closed container tend to evaporate, go into the gas phase. But as the gas phase becomes more concentrated, some of those particles collide with the surface of the liquid and re-enter the liquid phase. Initially, you might experience a slight decrease in volume, but it stays constant over time, because over time, the rate of evaporation equals the rate of condensation. That's dynamic equilibrium. The concentrations are not changing. You don't notice any change anymore. But that indicates you're at equilibrium. The rate going forward equals the rate in reverse. So check out this ammonia equation. We've got nitrogen and hydrogen forming ammonia. Check out this graph. Initially, we have no product. Initially, we have no ammonia. Initially, all I have are reactants. I have nitrogen and I have hydrogen. And they should be present, somewhat present, in the ratio of the balanced equation. There's more hydrogen than there is nitrogen. As this reaction progresses, the concentration of the 2 reactants will decrease and the product will increase. Look what happens once this is at a steady rate. Once equilibrium has been established, everything should be present at the stoichiometric ratio. So there would be like 3 parts hydrogen, 2 parts ammonia, 1 part nitrogen. The forward and the reverse happen at the same rate. So everything should be present at the ratio from the balanced equation. Which again, kind of look at this second graph. Initially, you've got this thing going forward. Initially, we form mostly products. But then once the products become more concentrated, now the reverse will start to pick up. Until eventually these rates become equal. That's equilibrium. When the rate of the forward equals the rate of the reverse reaction.